Welcome back to the video series entitled From the Ancient Greeks to Isaac Newton, Early Astronomers and the Birth of Science.
Lecture 2, Copernicus and Galileo.
I'm showing you here the stars of the next two lectures and where their lives fit on this timeline spanning the period of the Renaissance and of the Enlightenment. Before we get to Copernicus, I need to tell you a few things. First, I want to tell you about two important thinkers from the late Middle Ages. Second, I need to mention perhaps the most important invention from the time of the Renaissance. And finally, I want to set the stage for Copernicus by saying a bit more about Ptolemy's model. Robert Grose-Test and Roger Bacon were both English scholars and theologians. They both spent time at Oxford, and they are each remembered for their contributions toward advancing a theory of science. Among other things, Robert Grose-Test formulated and endorsed the concept of the controlled experiment. He also drew attention to the twofold nature of scientific reasoning, generalizing from particular observations to a universal law, and then reasoning back again from a universal law to the prediction of particular events. The first process consists primarily of inductive reasoning, while the second process involves primarily deductive reasoning. Roger Bacon, who came along a little bit later, provided perhaps the first succinct formulation of the scientific method. That is, theories supplied by reason should be verified by sensory data, aided by instruments, and corroborated by trustworthy witnesses. Next, I need to point out that the printing press was invented in 1436. Am I suggesting that the printing press had something to do with the scientific revolution? Absolutely. Thanks to the printing press, scholars were able to publish their works and share them with a whole growing community of scientists spread out over Western Europe. Compared with the time-consuming task of copying manuscripts, the printed word allowed an exponential increase in the efficiency of spreading knowledge. Within this extended network, academics had a basis for communicating back and forth, critiquing, debating, and expanding each other's ideas. The situation was analogous to the arrival of the first true alphabet, combined with an ever-expanding network of maritime trading centers in ancient Greece. Finally, in order to set the stage for the arrival of Copernicus, we have to say a bit more about Ptolemy's model. The ancient Greeks generally held geometry up as the abstract ideal after which the physical world was modeled. In particular, the circle with its perfect symmetry was something to be revered. And so their geocentric model was based on the firm belief that planets must move in perfect circles of uniform velocity. There was a problem here. Even when not in retrograde motion, the planets do not appear from Earth to move with uniform angular velocity. Now, we need to pause here and make sure we understand the concept of angular velocity. As a planet moves across the night sky over weeks and months, an observer on Earth can monitor that movement by way of an angle measured against the fixed stars. The angular velocity, omega, is simply the change in angular position divided by the change in time. The ancients found that omega for each planet was variable. The epicycles helped explain some of this variation, but not all. Here is a hypothetical example. Let's say this planet moves from the constellation Libra to Sagittarius, about 60 degrees, in 4 months' time. Several months later, it is observed to move from Aries to Taurus, only 30 degrees, in 4 months' time. Ptolemy's solution was to assume that the Earth was not quite at the center of this planet's circular orbit. So let's take Earth out of the picture for a moment. Let's assume the orbit is circular, with the center indicated here by the gray dot. And let's say that the planet travels at a constant angular velocity of 45 degrees every 4 months. Now, what if the Earth was located somewhat off-center? The angles measured during these two separate 4-month intervals would not be the same, even though the angular velocity relative to the true center of the orbit was a constant. This offset was known as the eccentric. With all this background in mind, it's time to introduce Copernicus. He was born in Royal Prussia in the Kingdom of Poland. He was a pretty smart guy. He earned degrees in astronomy, canon law, classics, and medicine from the universities listed here. He first sketched out his theory of a heliocentric universe in a short work known as the Commentariolus. He showed it to friends, but it was never published. By 1532, he had essentially completed De Revolutionibus Orbium Coelestium, his magnum opus containing the full exposition of his heliocentric model. However, despite urging from his friends, he was reluctant to publish it. The work was finally published in 1543, the year Copernicus died. The story goes that he first laid eyes on a printed copy when his friends presented it to him as he lay on his deathbed. He died peacefully later that day. His theory was revolutionary, but it was flawed. And it was flawed because he persisted in believing that all planets orbited in perfect circles with uniform angular velocities, just as his predecessors had supposed. So, if the Sun was truly in the center of all orbits, Copernicus faced the same problem that Ptolemy faced with his geocentric model. The data did not fit with uniform velocities. Here is the hypothetical example that I showed earlier, except now the Sun is at the center of the circular orbit. So, in keeping with Ptolemy's strategy, he had to take the Sun out of the center of the orbits. Then he assumed uniform angular velocities. In this case, 45 degrees every 4 months.
Then replace the Sun in a somewhat eccentric position in order to make his theory fit with observations. Copernicus did succeed in substantially reducing the size and number of epicycles required to explain observations, but he could not eliminate them entirely.
In the final analysis, after all these adjustments, if we look at how Copernicus's model matched up with actual observations, it performed better in some ways and worse in others, in comparison with Ptolemy's model. During the 60 years after Copernicus's magnum opus was published, it appears that only a minority of European astronomers endorsed the Copernican model. Among them were Galileo and Kepler. Meanwhile, certain Catholic and Protestant church leaders argued vehemently against the Copernican model. Philip Melanchthon, a close associate of Martin Luther, wrote, "Certain people believe it is a marvelous achievement to extol so crazy a thing, like that Polish astronomer who makes the earth move and the sun stand still. Really, wise governments ought to repress impudence of mind." As the three general reasons for rejecting the Copernican system, he cited the evidence of the senses, the 1,000-year consensus of men of science, and the authority of the Bible. For Melanchthon, if the earth were moving, Surely our senses would detect that motion. Despite criticism from multiple sides, in certain Roman Catholic circles, Copernicus's book was incorporated into scholarly curricula throughout the 16th century. For example, at the University of Salamanca in 1561, it became one of the 4 textbooks that students of astronomy could choose from, and in 1594 it was made mandatory. It was finally banned by the Catholic Church in 1616 in response to arguments put forward by Galileo in favor of the Copernican model.
In spite of the imperfections in the Copernican model, it did provide a framework for advances in understanding the motion of the planets. For one thing, it was now possible to calculate the true orbital periods of the planets, starting with the Earth.
Let's say we use Gemini as a reference direction. If Gemini is directly overhead at midnight, some night, as shown here in this diagram, and then directly overhead once again at midnight, 365 days later, then the orbital period of the Earth is 365 days. So that's easy. What about for the other planets? Let's take Mars as an example. Mars and Earth orbit the Sun at different rates. Earth's angular velocity is faster. Now, every so often, Mars is directly opposite the Sun relative to Earth. We say that Mars is in opposition. This event happens roughly once every 780 days. So, if we take this situation as the starting point, here is the situation 6 months later, and here is the situation following another 6 months, when the Earth has completed a full revolution. After a total of 18 months, Earth has now made 1.5 orbits around the Sun, whereas Mars is yet to complete a single orbit. In this diagram, we can see that Mars has now completed a full orbit, but from the perspective of someone on Earth, it is a little hard to confirm that fact because we don't know the radius of Mars' orbit. All we know is that Mars is lined up with Leo. Therefore, its actual position might just as well be as indicated here by the red dotted circle, in which case it has moved beyond one full orbit. Or its actual position might just as well be as indicated here once again by the red dotted circle, in which case it has not yet finished one full orbit. Eventually, Earth catches up to Mars until it is once again in opposition. 780 days have passed. Now, recall that the Earth does not quite travel 1 degree per day. Rather, it travels 360 degrees in 365 days. The Earth has traveled through approximately 769 degrees. That's 2 full circles plus 49 degrees. During that time, Mars has traveled 360 degrees plus 49 degrees. For a total of 409 degrees. In 780 days. That's an angular velocity of 0.524 degrees per day. Now, let P equal the orbital period of Mars. Then we can set up the equation. 360 degrees equals P times omega for Mars, that is, Mars' angular velocity. Once we plug in the angular velocity for Mars that we have determined, we can solve the equation for p. And it turns out that the orbital period for Mars is 687 days.
With the Copernican model, we can also calculate the radius of each planet's orbit relative to the radius of the Earth's orbit. We again use Mars as an example. Let's say we want to know the angle between Mars and Earth with the Sun as the vertex of that angle. Generally speaking, it's not possible to measure that angle directly. However, we do know that whenever Mars is in opposition to Earth, the angle between the two is 0 degrees. Now, if we go forward in time 1/2 cycle, or 390 days, Mars is directly behind the Sun, so the angle between Mars and Earth, relative to the Sun, is 180 degrees. And after an additional 195 days, or 1/4 cycle, we can deduce that the angle between Mars and Earth will now be 90 degrees. This allows us to construct a right triangle, as shown here. We want to know the angle theta, and that's an angle that we can measure directly. So, if we let r sub m equal the radius of Mars' orbit and r sub e equal the radius of Earth's orbit, the ratio of r sub m to r sub e is simply the tangent of theta. With this information in hand, you can construct a model of the solar system showing the relative distance of each planet from the Sun. And you can match each planet up with its orbital period, as shown in this table. One immediately sees that the greater its distance from the Sun, the longer its orbital period. There is a relationship here. In mathematical terms, the orbital period depends on the orbital radius, or a planet's orbital period is a function of its radius. We could write it this way. Let r equal the distance from the Sun, let p equal the orbital period, and then p equals a function of r. Imagining a mathematical relationship of this type was something new, and it became a core principle and sine qua non of the scientific revolution. Copernicus believed that nature was essentially mathematical in its structure, and that only the power of mathematics could reveal the true nature of the planetary system. Next time we will see how Kepler builds on this concept. Spoiler alert, here is Kepler's third law. P squared equals some constant times r cubed, or P equals the square root of k times r cubed. We now turn our attention to Galileo. Many, including Einstein, have called Galileo the father of modern science. He didn't exactly invent the scientific method, but he did perhaps more than anyone before him to demonstrate its power. Like Copernicus, he believed that nature is essentially mathematical in its structure. He famously said, "Mathematics is the language in which God has written the universe." Also like Copernicus, he suspected that the geocentric model was wrong. Unlike Copernicus, or anyone else before him for that matter, he found a way to prove that it was wrong. When Galileo found out about the invention of the telescope, he set out to make successive improvements in its design, so as to increase its magnification. As a result of his improvements, for the first time the telescope became a useful instrument for astronomers. Galileo himself used his telescopes to study the night sky. One of his projects was to study the phases of Venus. Now, if you study Venus over time, you will know that for periods of time, Venus is a little bit east of the Sun, and we see it in the evening after the Sun is set. During other periods of time, Venus is a little bit west of the Sun, and we see it in the morning before the Sun has risen. At other times, Venus is so close to the Sun that we can't see it at all. Let's visualize how the Ptolemaic model would explain these observations of Venus. Recall that Venus's orbit contains epicycles, whereas the Sun's does not. I have indicated the center of Venus's epicycle with a gray dot and labeled it C. Venus circles C in a clockwise direction from the vantage point of this diagram, while C and the Sun circle the Earth in a clockwise direction as well. From the vantage point of Earth, C is always lined up with the Sun, whereas the position of Venus relative to the Sun is constantly changing as a consequence of its epicycles. In the arrangement shown here, Venus will appear to someone on Earth as somewhat eastward of the Sun, whereas in the arrangement shown here, Venus will appear to someone on Earth as somewhat westward of the Sun. When Galileo first looked at Venus, he might have seen this, a crescent shape. Now, assuming that Venus, like the Moon, is visible in the night sky only because sunlight is reflecting off of it, the Ptolemaic model would predict that Venus, when visible at all, would always appear to us as a crescent. As this diagram shows, within the Ptolemaic framework, the crescent will appear thicker or thinner depending on the position of Venus relative to the Sun. But we will never see Venus half full or anything more than half full. However, as Galileo viewed Venus over many months, he saw something that Ptolemy could not have predicted. Galileo found, in fact, that sometimes Venus was a slim crescent, sometimes it was half full, and sometimes it was clearly more than half full. This can only happen if Venus is revolving around the Sun, so that sometimes it is behind the Sun from our vantage point. This observation was really the final nail in the coffin of the Ptolemaic model. The phases of Venus was not the only revolutionary observation that Galileo made with his telescope. His discovery that Jupiter was orbited by several moons, and that the Milky Way was not just a luminous cloud, but instead was entirely composed of individual stars, likewise shattered long-held conventional beliefs. Moreover, his pioneering use of the telescope was only one of his several major contributions to the advancement of science. In fact, when we first think of Galileo the scientist, most of us probably picture him dropping balls of different weights off the Leaning Tower of Pisa. It's not clear if Galileo actually did these experiments himself, but similar experiments were being done, and Galileo was aware of the results. Two balls of different weight and different mass will fall at the same rate. This finding contradicted the teachings of Aristotle, who would have said that the heavier, more massive ball would fall faster. Now you might say, so what? Well, this was a big deal because up until the time of the scientific revolution, Aristotle was generally considered to be the authority on everything. Now, scientists were willing and eager to question that authority. But there's still more to the story. Galileo wanted to learn more about how quickly objects accelerate as they fall to Earth, but he realized that there were at least two sources of error. First, he knew about air resistance, and more generally, he knew about friction. Also, objects falling straight down accelerate so rapidly that the timekeeping devices of that era could not accurately measure the time elapsed during the fall. Galileo realized that he needed to minimize friction and slow things down. So he decided to study balls rolling down ramps where he could control the speed of movement. Galileo needed an accurate timekeeping device. Some sources say he used a water clock, some say he used his pulse, and still others say he used a pendulum. The first mechanical clocks regulated by a pendulum were not developed until a half a century or so after Galileo. Only then was it possible to accurately measure time intervals in seconds. As we try to reconstruct what Galileo did, let's just assume that he used a simple pendulum. I want to emphasize four key takeaways from Galileo's analysis of falling bodies. First, acceleration of a falling body is uniform, that is, constant. Although Newton would ascertain that in fact acceleration due to gravity is not uniform, Galileo's claim is true to a very good approximation near the surface of the Earth. Second, acceleration of a falling body does not depend on the mass of the body. Galileo confirmed this claim experimentally, and Newton's second law and his universal law of gravitation provided a theoretical basis accounting for this observation. Third, the principle of inertia. Galileo wrote, "Furthermore, we may remark that any velocity once imparted to a moving body will be rigidly maintained as long as the external causes of acceleration or retardation are removed, a condition which is found only on horizontal planes. For in the case of planes which slope downwards, there is already present a cause of acceleration, while on planes sloping upward, there is retardation." So this is the law of inertia, which Galileo mentions almost in passing, as if it is too obvious to merit an extended discussion. And yet the statement is once again in clear contradiction to Aristotle's claim that all moving bodies on Earth come to rest unless a force is continually applied to them. We can imagine Galileo somewhat surprised to learn that both Descartes and Newton considered the principle so fundamental that they each made it their first law of motion. One might argue that Galileo's statement does not refer at all to bodies at rest, but this criticism is specious, because Galileo understood that whether a body is at rest or moving uniformly depends only on the reference frame of the observer, as we shall soon see. Finally, d is proportional to t squared. That is, the distance traveled by a falling body under constant acceleration is proportional to the square of the time interval. Galileo arrived at this fourth takeaway by experiment, but also logically from first principles. Let's consider the theoretical result first. Let's list Galileo's premises or first principles. There are three of them. Galileo expressed mathematical relationships in words and with geometrical figures. Algebra had just been introduced to Western Europe, and it was not yet the convention to express mathematical relationships with numbers, variables, and the symbols of arithmetic. So Galileo wrote, regarding uniform motion, "By steady or uniform motion, I mean one in which the distances traversed by the moving particle during any equal intervals of time are themselves equal." We could express it this way. Let v sub c equal constant velocity and delta x equal the distance traveled. Then V sub c equals delta x divided by delta t, and delta x equals V sub c times delta t. It is useful to think of distance traveled as a change in position. X is a position coordinate, and we are talking about motion in one direction only, so we only need one position coordinate. Premise number 2, uniform acceleration. A falling body accelerates uniformly. It picks up equal amounts of speed in equal time intervals, so that if it falls from rest, it is moving twice as fast after 2 seconds as it was moving after 1 second, and moving 3 times as fast after 3 seconds as it was after 1 second. We could write, let a sub c equal constant acceleration, then a sub c equals delta v divided by delta t, and delta v equals a sub c times delta t. Premise number 3 is known as the mean speed theorem. The time in which any space is traversed by a body starting from rest and uniformly accelerated is equal to the time in which that same space would be traversed by the same body moving at a uniform speed whose value is the mean of the final speed and the speed just before acceleration began. We could write, let velocity at rest, v sub naught, equals 0, and final velocity, v sub f, equal a sub c times delta t, and mean speed, v sub m, equal 1/2 times the quantity v sub f minus v naught. Then delta x equals v sub m times delta t, which in turn equals 1/2 times v sub f times delta t. Galileo apparently felt that the mean speed theorem was self-evident once he constructed the following geometric argument. This is the relevant illustration from his final book, Dialogues Concerning Two New Sciences. Well, let's rotate it. Now let's flip it and add a pair of axes so it looks more familiar to us. The horizontal axis represents increments of time, and the vertical axis represents velocity. The red line is the velocity of a uniformly accelerated body over a period of time, delta t. The dotted line represents the final velocity. And v sub m is the mean velocity equal to 1/2 of the final velocity. The rectangle shaded in green has a height of v sub m and a width equal to the total elapsed time, delta t. Since the area of this rectangle is the product of v sub m and delta t, the area indicated the total distance traveled. In general, the distance traveled by any body moving with uniform velocity will equal the area of the rectangle constructed in the same manner, bounded above by the horizontal line representing the velocity, and to the right by the vertical line representing the total elapsed time. Any mathematician would grant that this claim is self-evident based on the definitions of velocity and the area of a rectangle. Galileo extrapolated that the distance traveled by a body moving with uniform acceleration was here again equal to the area bounded above by the line representing the velocity, in this case the red line, and to the right by the vertical line representing the elapsed time. However, many mathematicians before and after Galileo felt that a more rigorous proof was needed. The ultimate mathematical validation of the mean speed theorem would have to await the development of the basic principles of calculus. In any case, Galileo's next step was simply to demonstrate that the area in blue equaled the area in green, which he did by pointing out that the area now shaded in purple equaled the area now shaded in pink, whereas the areas now shaded in green and blue are identical. Let us accept the mean speed theorem is true and return to a demonstration based on the rules of algebra. From our premises, we have established two key relationships. They are circled in green here. Let's take them into some clean workspace. Let's condense the second equation. And now let's substitute for v sub f in the second equation. This will give us this equation, which of course we can simplify to delta x equals 1/2 times a sub c times delta t squared. Since acceleration is a constant here, we have shown that the distance traveled, delta x, is proportional to the square of the time elapsed. Now let's see how Galileo confirmed this finding experimentally. He has set up his ramp and he is using a pendulum to mark time. Galileo defines his unit of time, 1p, to equal the time for the pendulum to complete one full swing back and forth. He lets the ball go and determines its new position after 1p. The distance traveled in 1p defines his standard unit of length, 1 gal. He begins to fill in a table. He repeats the experiment and finds that in 2p's, the ball travels 4 gals, and that it travels 9 gals in 3p's, 16 gals in 4p's, and 25 gals in 5p's. From the table, it is clear that d, or delta x, is proportional to t squared. Notice that by defining or deriving all the relationships between acceleration, velocity, time, and distance theoretically, he has simplified the experimental task. From the theory, he has predicted the relationship between time and distance, so that those quantities are the only ones that he has to actually measure in order to confirm or refute the theory. As we have just seen, these experiments led Galileo to develop his concept of inertia, and this concept helped him to offer a rebuttal to those who continued to argue in favor of a geocentric model of our solar system. According to Galileo and Copernicus, the Earth moves. It moves around the sun. Those who refused to accept this proposition relied heavily on the argument that our senses give us absolutely no indication that the Earth is moving. Some of these skeptics, when confronted with the evidence provided by Galileo's observations of Venus, accepted the proposal of Tycho Brahe that Venus and Mercury orbit the Sun, but the three of them as a group, along with the other planets, orbit the Earth. In this so-called hybrid model, the Earth is an unmoving center of celestial motions. Nevertheless, Galileo remained steadfast in his position because he understood that scientists should not always trust their senses, and he did a thought experiment to convince himself, and perhaps others, that our senses might be misleading us in regard to whether the Earth moves or not. His thought experiment was founded on a concept of inertia and on consideration of how different frames of reference influence our perception of motion. Here is an updated version of Galileo's thought experiment. From our point of view, the trolley is moving to the right at a constant velocity. The boy throws a ball up in the air. As long as the trolley is not accelerating, from his perspective, the ball simply goes straight up and then straight down. If he were in an enclosed boxcar with no windows, for example, he would have no way of knowing from any immediate evidence or from any experiment that he might do that he was moving to the right relative to the neighboring environment just outside the boxcar. The situation is similar for us standing here on our planet, unable to detect the motion of the Earth. Of course, to an observer standing on the ground nearby, the ball follows a trajectory composed of both vertical and horizontal motion. The formal concept of vectors had not yet been invented, but Galileo clearly thought in terms of vector quantities. Let me clarify. The ball's initial velocity vector, that is, its initial speed and direction, according to observer B, can be found by adding vectors. To add vectors, we are allowed to move them around in vector space. Vector space is not a physical space. It's a conceptual space represented in a diagram. It's easy. Let me show you. First, we move the blue vector into vector space, maintaining its same orientation and magnitude. Next, we move the red vector into vector space, placing its tail on the head of the blue vector while maintaining its magnitude and orientation. Now we can add these two vectors to get a resultant vector by following a simple rule. We construct a vector with its tail on the tail of the blue vector and its head on the head of the red vector to produce our resultant vector, the purple vector shown here. Now we can move the purple vector back into our original diagram and place its tail at the point where the ball leaves the boy's hand. And we can now see the initial velocity vector as perceived by observer B. In other words, all motion of constant velocity, as perceived through our senses, is measured relative to some inertial reference frame. An inertial reference frame is a reference frame that is itself not accelerating. Otherwise, our choice of a particular reference frame is arbitrary. Both the boy's reference frame and the girl's reference frame are perfectly valid reference frames. This is Galilean relativity. As an aside, Einstein will take Galilean relativity as a starting point and make one simple tweak, proposing that the speed of light will always be observed to be the same regardless of the reference frame, and his theory of special relativity will be born. You are now prepared to proceed to Lecture 3, Brahe and Kepler.